In the mathematical field of set theory, a large cardinal property is a certain kind of property of transfinite cardinal numbers. Cardinals with such properties are, as the name suggests, generally very large. The proposition that such cardinals exist cannot be proved in the most common axiomatization of set theory, namely ZFC, and such propositions can be viewed as ways of measuring how much beyond ZFC one needs to assume to be able to prove certain desired results. In other words, they can be seen, in Dana Scott's phrase, as quantifying the fact that if you want more you have to assume more. There is a rough convention that results provable from ZFC alone may be stated without hypotheses, but that if the proof requires other assumptions, these should be stated. Whether this is simply a linguistic convention, or something more, is a controversial point among distinct philosophical schools. A large cardinal axiom is an axiom stating that there exists a cardinal with some specified large cardinal property. Most working set theorists believe that the large cardinal axioms that are currently being considered are consistent with ZFC. These axioms are strong enough to imply the consistency of ZFC. This has the consequence that their consistency with ZFC cannot be proven in ZFC. There is no generally agreed precise definition of what a large cardinal property is, though essentially everyone agrees that those in the list of large cardinal properties are large cardinal properties. Partial definition. A necessary condition for a property of cardinal numbers to be a large cardinal property is that the existence of such a cardinal is not known to be inconsistent with ZFC, and it has been proven that if ZFC is consistent, then ZFC plus no such cardinal exists, is consistent. Hierarchy of consistency strength. A remarkable observation about large cardinal axioms is that they appear to occur in strict linear order by consistency strength. That is, no exception is known to the following. Given two large cardinal axioms A1 and A2, exactly one of three things happens. ZFC proves ZFC plus A1 is consistent if and only if ZFC plus A2 is consistent. ZFC plus A1 proves that ZFC plus A2 is consistent, or ZFC plus A2 proves that ZFC plus A1 is consistent. These are mutually exclusive, unless one of the theories in question is actually inconsistent. In case 1 we say that A1 and A2 are equiconsistent. In case 2, we say that A1 is consistency-wise stronger than A2. If A2 is stronger than A1, then ZFC plus A1 cannot prove ZFC plus A2 is consistent, even with the additional hypothesis that ZFC plus A1 is itself consistent. This follows from Gödel's second incompleteness theorem. The observation that large cardinal axioms are linearly ordered by consistency strength is just that, an observation, not a theorem. Also, it is not known in every case which of the three cases holds. Saharan Scheller has asked, is there some theorem explaining this, or is our vision just more uniform than we realize? Wooden, however, deduces this from the omega conjecture, the main unsolved problem of his omega logic. It is also noteworthy that many combinatorial statements are exactly equiconsistent with some large cardinal rather than, say, being intermediate between them. It should also be noted that the order of consistency strength is not necessarily the same as the order of the size of the smallest witnessed way. Large cardinal axiom. For example, the existence of a huge cardinal is much stronger, in terms of consistency strength, than the existence of a supercompact cardinal. But assuming both exist, the first huge is smaller than the first supercompact. Motivations and epistemic status. Large cardinals are understood in the context of the von Neumann universe phi, which is built up by transfinitely iterating the power set operation, which collects together all subsets of a given set. Typically, models in which large cardinal axioms fail can be seen in some natural way as submodels of those in which the axioms hold. For example, if there is an inaccessible cardinal, then, cutting the universe off at the height of the first such cardinal yields a universe in which there is no inaccessible cardinal. Or if there is a measurable cardinal, then iterating the definable power set operation rather than the full one yields Gödel's constructible universe. L, which does not satisfy the statement, there is a measurable cardinal. Thus, from a certain point of view held by many set theorists, large cardinal axioms say that we are considering all the sets we're supposed to be considering, whereas their negations are restrictive, and say that we're considering only some of those sets. Moreover, the consequences of large cardinal axioms seem to fall into natural patterns. For these reasons, such set theorists tend to consider large cardinal axioms to have a preferred status among extensions of ZFC, one not shared by axioms of less clear motivation or others that they consider intuitively unlikely. The hardcore realists in this group would state, more simply, that large cardinal axioms are true. This point of view is by no means universal among set theorists. Some formalists would assert that standard set theory is by definition the study of the consequences of ZFC, and while they might not be opposed in principle to studying the consequences of other systems, they see no reason to single out large cardinals as preferred. There are also realists who deny that ontological maximalism is a proper motivation, and even believe that large cardinal axioms are false. And finally, there are some who deny that the negations of large cardinal axioms are restrictive, pointing out that there can be a transitive set model in L that believes there exists a measurable cardinal, even though L itself does not satisfy that proposition.